Hello, my name is Olivia LaFond, and today I'm going to be sharing my research with you for my device called the tapeworm. To better understand why this research is important, we have to take a closer look at the small intestine itself. The small intestine is approximately 22 feet long and comprises about 75% of the GI tract. Due to its length and location in the middle of the tract, it makes it the least accessible segment. Looking on the right, we can see a diagram of the digestive tract and the tapeworm device within that tract. Taking a closer look, we can see how the tapeworm may appear from within the small intestine. We can also look at a transverse cross-section of the small intestine, showing how the tapeworm would be ideally positioned within the layers. With direct access to the small intestine, this reduces the need for invasive procedures and frequent testing in patients with chronic illnesses. Very few options provide multifaceted treatment in one product. My goals were to develop a device for long-term monitoring and drug delivery in the small intestine that has safe, long-term attachment to the small intestinal wall, adequate retention force while minimizing discomfort during attachment and removal, internal actuation with biocompatible extendable hooks effective in any orientation. Moving on, we can take a look at the device prototype. The first part is a 3D printed device casing, which is made of PLA or biocompatible resin. The device is deployed through spring-based actuation. This works by a spring compressed by an isomote layer. Once the isomote layer degrades, the spring decompresses and pushes the hooks out into the small intestine. One important feature of this design is that the hooks are channel guided. These channels are set to ensure that the hooks deploy in an exact direction and spacing needed. On the right, you can see the device fully deployed. Here, the spring has decompressed and the hooks extend outward at set angles determined by their channels. Now, moving on to experimental methods, we can take a look at how we ran these tests. Our main point of these experiments were hook and device retention validation. The three main tests were focused on retention testing, insertion force testing, and organ model testing. Now, to our first results. We can see the retention force compared between orientations. On the left, we have our upwards orientation, and on the right, we have our downwards orientation. Comparing orientations, on the left, you can see the upwards orientation, as it's being pulled with the hooks in the same direction as the force applied. On the right, we can see the downwards orientation, where the hooks are being pulled against the force applied. Figures 1 and 2 show the device retaining securely regardless of orientation, withstanding digestive forces that exceed approximately 0.3 newtons generated by peristalsis, confirming stable anchoring in either orientation. Our next result shows the hook retention force. Figure 3 shows the 15 millimeter straight stainless steel hooks fully inserted, withstanding up to 16 newtons of force before loosening from the intestinal wall. This far exceeds the force generated by the digestive process, demonstrating the hook's ability to maintain retention within the small intestine. Figure 4 shows the average insertion force for different hook designs: the straight 18 millimeter hook, curved 18 millimeter hook, and straight 15 millimeter hook. We can see from Figure 4 that it shows that the straight 15 millimeter hook generated 2 newtons of force, which exceeds the 0.7 newton penetration threshold, validating the use of the straight 15 millimeter hook's design, as it is the most simple compared to the other prototypes in terms of manufacturing. Finally, Figure 5 shows the shear retention force during peristaltic motion. We can see the forces compared between our 100%, 50%, and 25% inserted hooks. This figure shows that even at 25% insertion, each hook alone withstands approximately 0.4 newtons, exceeding the 0.3 newton peristaltic force and ensuring stable retention. For future work, we need to test the deployment in GI conditions, test the biocompatibility and biodegradability of the system and its components, and test ex vivo deployment, retention, and expulsion with histological results for tissue damage. Thank you so much for listening, and I hope you enjoyed my research. Thank you again.